For our last short answer from Unit 3, we're going to deal with a roller coaster with a circular loop. A designer's working on a new roller coaster, and she begins by making a scale model. On this model, a car of total mass 0.5 kilograms moves with negligible friction along the track in the figure shown. The car is given an initial speed of 1.5 meters per second at the top of the first hill, which has a height of 2 meters. Point A is located at a height of 1.9 meters at the top of the second hill, the upper part of which is a circular arc of radius 0.95 meters. So we're going to find the speed at point A for part A. So this is a straight up conservation of energy question. Gravity is the only force, and if we include Earth, it's internal to the system. So I can say K plus UG equals K plus UG. Just being clear that we're at the start here and we're at point A here. So 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. The mass of the car is 1/2 kilogram. The velocity at the beginning is 1.5 meters per second. The height at the beginning is 2 meters. The height at the end is 1.9 meters. And we're looking for the velocity. So a little bit of algebra there can give you that the final velocity is 2.1 meters per second. 4 points on that rubric. One's for bringing up conservation of energy. One's for having a good equation. One's for having the correct substitution. So all of those need to be correct. 1 point for your correct answer. So 4 points there. Part B, we're going to draw a free body diagram of the cart at point A, right? So at point A, we have gravity acting down and the normal force acting up. I drew this wrong the first time. This is not a cart inside a loop. I had to look back at the picture. It's going up and over the top. So the normal force is pushing up there at point A. So I got sucked into that originally, so don't feel bad if you did, but learn the lesson that we got to look at the drawing as well. So that's it for part B. We get 1 point for each correctly drawn and labeled force, so 2 points total, minus 1 point if you draw anything extra. Okay. So here's one we've done before. Calculate the magnitude of the force of the track on the car at point A. Guess what? They're just talking about the normal force, aren't they? Okay. So the net force here is going to be towards the center of that circle. So the net force is going to be down, right? So we're going to have to say down minus up equals net force. Okay, so down is mg, minus up is Fn, and the net force is centripetal, so it's mv squared over r because we just figured out the speed at the top there. So the normal force, after moving the normal force over here and that over here, we get mg minus mv squared over r. M is equal to 1/2 kilogram. The velocity we just figured out was 2.1 meters per second. And the radius of this circle is 0.95 meters. We get that off the drawing. So the normal force at the top there is 2.7 newtons. And just a side note there, it is less than the weight of the car. You felt that before. When you go over a hill, you feel a little bit lighter. That's because the normal force is, which is how heavy you feel, is less. So we get 1 point for indicating that the sum of the forces is centripetal, 1 force for having the correct relative signs, that is normal force and gravity have opposite signs there, 1 point for a correct substitution to get the correct answer. All right, part D. In order to stop the car at point A, some friction must be introduced. calculate the work that must be done by the friction force in order to stop the car at point A. So you might realize that we don't really have a way of calculating work over this distance, and we don't even really know what the distance is. But what do we know? What do we know work is equal to? Work is equal to a change in kinetic energy. So the kinetic energy at point A, right, that's how much it has, is 1/2 mv at A squared, which is 1.1 joules. Whoops, 1.10 joules, right? This is the mass of the block, and this is the velocity we calculated a couple steps ago. So that's how much kinetic energy it has. Well, that's how much work you needed to do in order to stop it. Okay, so we get 1 point for indicating that the work is equal to the kinetic energy, 1 point for the correct substitution, and 1 point for the correct answer. Now, it does say how much work must be done by the friction force. So for me, that answer should be positive, although technically the friction is doing negative work. So you might want to indicate something like that in your answer as well. So there's another example that I keep telling you guys is going to come up. They give you something that you can't calculate, but you've got to realize what that's equal to and then go from there. Finally, for part E, which is actually ended up being worth a lot of points, explain how to modify the track design to cause the car to lose contact with the track at point A before descending down the track, and justify your answer. So there's a couple of ways we can do this, but the point is, if the car loses contact, then Fn equals 0. And we've done that a couple of times before. Now we came up with an expression for the normal force a couple of steps ago, mg minus mv squared over r. So what we need to do, this is given. We can't really change anything there. So we want to make this term bigger. Okay? We want to make this term bigger. So in order to do that, we could do two things. We could, in order to make this fraction big, I can make this radius smaller because that's on the bottom there. So what does that mean? That means make a tighter loop. Okay, make a tighter loop. What happens here is that this second term gets bigger and it decreases the normal force. The other way we could do it is we could make this velocity larger. Well, how do I do that? Going back to the problem setup, the only way that I could, I guess I could do that a couple of ways, although it says modify the track design. So my first thought was, make the car go faster at the beginning, but that's not modifying the track design. But what we could do is make that initial hill higher. That would also increase this term and drive this whole thing closer to 0. So how did that work? 1 point for indicating that we could make that the radius needs to be smaller. That means a tighter loop. That would then refer to this equation here for another point. And then indicating that the cart will lose contact when the normal force is less than or equal to 0. Or you could indicate that when the normal force is equal to 0, they lose contact with the hill, making the first hill higher, and then saying that for either one, the speed at A will be greater. So there's 3 different ways. I guess there's 2 different ways for 3 points. Let me try to say this again, and I'll type it up for you guys as well. The first way to get the 3 points was smaller radius here, then referring to the normal force like this, and then saying that the cart will lose contact when n equals 0. The second way to 3 points says make the first hill higher, refer to this, and then say that the speed at A will be greater. So there were a couple different ways to go about that, but 3 points if you got to that. So that's it for Unit 3 short answers.